now we're going to see a new type of network, a new kind of layer, which are these convolutional networks. And they are very used for image processing, but they are also useful in general for all problems where you're trying to identify patterns in the data, but the pattern can be placed in any position on your data vector. So this can be processing sounds, things like 3D scans or things like that. So you can do this in several different dimensions, but it's useful for any problem where you have a large vector for each example, and somewhere around there are patterns that you're interested in. So I'm going to talk a bit what is convolution, how we use convolution layers in networks, and this alternation between convolution and pooling, and then seeing how we can use this for classification. And then we're going to go back to the Keras Sequential API, continue this introduction to Keras, the sequential model here, by looking at a regression problem and an image classification problem using this fashion-list dataset. So convolution mathematically is the integral of the product of two functions inverting one of the functions. So we have this integral with respect to tau, and we take the f of tau and g of t minus tau, and we are integrating this where we have this idea that the functions change over time. So this mathematically in abstract is difficult to try to understand why it's used for, but it's one good example is this linear time invariant systems. So suppose that we have one of these systems. This linear means that it has a linear response. Time invariant means that the kind of response occurs wherever it may happen in time. So imagine that you have an iron bar and you can hit it with a hammer or something like that, and this would be an example. It's linear because the stronger the impact you have, the more it will oscillate. So this amplitude will change linearly with the input, the impulse you give it. And it's time independent because it can wait for a few hours, and only when you hit it with a hammer will it start vibrating. So let's suppose that this is the response of our iron bar when it receives some impulse, and we want to know what happens if we strike it twice with the hammer quickly. So this can be, for example, in seconds, and we strike it at second 1, and then 0.2 seconds later, so 2 quick taps. How will it oscillate if we do that, and if the response is this one? We can do this by taking the symmetric of the response and then doing the convolution here. So we can imagine that we are changing over time the displacement between the symmetric of the response and the impulse we gave there, and we are computing the integral of that for each instance. So this gives us the convolution as a function of time as the integral of those two things. And when we look at the convolution, we see this. Nothing is happening until we hit it with the first strike of the hammer. Our bar starts oscillating, but then we hit it with the second one, and it oscillates like this. So this is an example of how we can use convolution to bring together these two functions, the response and the impulse that we are giving to the system. We can also do it the other way around, and this is a better idea for convolutional networks, where we want to detect some pattern. So suppose that we are receiving this signal and we want to detect when this pattern of spikes occurs. We can create a detector function that this is inverted or not. No, it doesn't matter much in practice there, but let's consider the same kind of equation, and we are inverting the detector function. And now we compute the integral of this product with one of them inverted as a function of time. And you can see that at this time, when the pattern we want did not appear yet, we don't have much of a signal here in the convolution. But when we start getting overlaps here, we start having peaks on the convolution, and the highest one corresponds to when the pattern appeared in our signal. So we can create convolutions to detect patterns in the data that can appear anywhere along those vectors. And this is the basic idea for convolutional networks. So what we can do this is in the continuous case. We can think of the discrete equivalent, discrete convolution, when instead of having continuous functions, we have a vector of values and a vector for our detector. So this is generally what happens in convolutional neural networks. We are doing the discrete convolution. And the idea here is that we have a kernel. This is a tensor. It can be a vector if we are dealing with one dimension. It can be a matrix if we are dealing with two dimensions. With images, it's usually a tensor because images have stacks of different colors. A color image is three matrices, one for red, one for green, and one for blue. So we need parameters for all of those. But in any way, this tensor with the parameters is the kernel, and we're going to multiply these weights by values in the input that we are getting. So in one dimension, it would be something like this. We can imagine that our kernel is 0 everywhere except in some small region, and we can do this over all the image. Or we can simplify this and look only at the place where the kernel is not 0 and ignore the rest. So in practice, we don't need to actually do the sum over from minus infinity to infinity. That would be wasting a lot of time. So in practice, you can imagine that for a convolutional neural network, you have this set of values, this kernel, that you're going to multiply in one region of the input, and then you're using the same thing on another region of the input, and so on, to do the equivalent of what we saw here, this translation on this axis. So actually, we generally use the kernel in the coordinates and the displacement on the input. For example, if it's a two-dimensional image, we can do it like this, and we imagine that we are scanning the kernel over the image. And we are actually not doing a convolution. Convolution is commutative because we use this inversion of the coordinates on one of the functions, and that makes it commutative. In practice, we are not doing the inversion. There is no point in doing that because inverting the kernel will be just the same as using different parameters. And if the parameters are learned by the network, we are not worried with that. So actually, this is called a cross correlation when you don't do the inversion. But for convolutional networks, that doesn't matter because the parameters will be whatever the network learns. And that's why we call them convolution. But if you want to be rigorous about it, it's actually a cross correlation. But the general idea is that we have this kernel that we are going to scan through the input. The kernel has different weights that are going to be multiplied by the input, and then everything summed up, which is the equivalent of these sums or these integrals here. And those will serve to identify patterns in the data. So if the correct pattern matches whatever the kernel is trying to look for, we will have a high output. If it's not, we will have a lower output. So this is the basic idea for convolutional neural networks. The advantage with respect to dense networks is that we have much sparser connectivity because each kernel is only looking for a small part of the input. We don't have weights for all the input at the same time. And we have effectively shared parameters because when we are sliding the kernel through the input, this is the equivalent of having different neurons using always the same parameters. So we don't have to adjust parameters, many parameters independently. This results also in equivariance, which is a change in the input in the translation will result in the same change in the output of the convolution layer. So I'm going to talk a bit more about this. The idea of these sparse interactions is that if you have an input and a dense layer, like we did before, you have waves connecting all the values of the input to all the neurons on the dense layer. But if you are using a convolutional kernel with, say, 3 of size here, then you only have connections between the input and between each neuron and 3 of the inputs, or 2 in the extremity. So you have far fewer connections, and in addition, these connections are shared. So you don't see very well here. I'm going to use this projector is not very good, but this connection here that is connecting this input to this neuron is actually the same as this connection connecting this input to this neuron and so on, because this is always the same kernel that we are applying here. So one big advantage of convolutional neural networks is that they have far fewer parameters than what the equivalent dense network would be for the same size. And this can improve a lot the results and training. Even though we have this limited field of this receptive field for each neuron, for example, this neuron only receives inputs from these three values here. When we stack convolutional layers using the same receptive field in this case, these neurons deeper in the network can actually receive input from a larger fraction of the input factor. So, in effect, the receptive field of convolutional neurons deeper in the network can be very large, depending on the layers that we have. The equivariance idea can be seen here. For example, suppose that we have this very simple edge detection kernel that just multiplies one pixel by -1 and adds to the other. So basically, it has a higher response when there is a change in brightness of the image. And this works as an edge detector. You can see here low values, high values, and so on, and you can detect changes between bright and dark, and then dark and bright again, and so forth. So this would be the feature map generated by passing this kernel through the image. And the equivariance property here is that if we imagine changing the position of the images slightly to the right or to the left, this would result in the same feature map, but just changed a bit to the right or to the left. So the output of the convolutional layer can change along with the change in the input, as long as it changes in translation. If you rotate, then things are a bit trickier, because convolutions don't automatically adapt to that. But for translations, you can see that there is this equivariance between the feature map, which is the output of that kernel, that convolution operation, and the input that you're giving. So this is how things work in practice. These are called receptive fields, the area where each neuron is receiving inputs from at each time are called receptive fields, as an analogy with the neurons in the brain, in the visual cortex, that receive information from some neurons in the retina. And what we are doing here is, suppose that we have these weights in our kernel that are marked here in red, so 1, 0, 1, and so on. And this is the input, and we are passing this neuron over the whole input, and we are doing the multiplication and the sum, as we saw before, and this will produce for each position one particular value. So this would be the feature map that we are obtaining for one neuron here. If we have a different neuron with different weights, we get another different feature map, and so on. So in this case, if we are using 5 neurons here, we scan through the image and we obtain 5 feature maps, depending on each one a function of the weights on the kernel. So in this case, since the receptive field is 3 by 3 here on the input, each of these kernels has 9 parameters that we need to adjust. So usually we are going to apply multiple convolution filters. So we can start with the image. We apply use a number of neurons here on the convolution layer. So we obtain a number of feature maps. And now we can do this again and again and again in different layers. In each case, for example, here we have 5 neurons. So we are producing 5 feature maps. And then each feature map will have a height and a depth depending on the size that we get here, on the stride of the convolutions, and so on. Note that if we have here, for example, 4 feature maps, each of these neurons is going to receive data from all the depth of these feature maps inside its receptive field. So suppose that this was a color image. We would have 3 layers here, red, green, and blue. And so each of these kernels, if it's 3 by 3 on the pixels, would have 27 parameters. So it's 9 plus 9 plus 9, because they are receiving from red, green, and blue. But in any case, this is a far smaller number of parameters than what you would have if you did this with a dense network that would connect everything. Since the convolution is a linear transformation, we cannot just stack convolutions, because that in the end is just a linear transformation. We need to put some activation function there, and again, rectified linear units is a good idea for these hidden layer activations. Now, for the convolution layer, there are some parameters that we can adjust. The convolutional layer has a number of filters, so the filters will be the convolution kernel plus the activation function. This is the filter that produces the feature map. And by choosing a different number of filters, we are increasing or decreasing the depth of the convolution layer here. Then we can change the strides. So the stride is how far the convolution jumps at each step. In this case, we are using a stride of 1. It's jumping 1 position in each step. Here we have a stride of 2, so it's jumping 2 positions, and we can do that, for example, to get data from that receptive field, but then produce an output that is smaller than the input. Another thing that we may need is padding. Note here in this example, since we cannot put the kernel outside the input matrix, the feature map is smaller than the input matrix, because we are losing places in the edges. So if you don't do something to prevent this, each time you apply convolutions, things start shrinking because you cannot go outside the matrix. Padding prevents that by keeping the same size, for example, by adding zeros around here, and so we can now reach every place with the center of the kernel. So in this case, the feature map would have the same size as the input, the original input matrix. So this is another parameter that you can use. This is an example of a real convolution network. You have a convolution layer here with a number of filters and rectified linear unit activation. Then another one. Then we have pooling. Pooling shrinks the size by averaging or adding the different, or taking the maximum value and so on. I'm going to talk a bit about that. But then we have 2 convolutions and then pooling and so on. And then here we have a fully connected network that does the actual classification. So generally, when we use this for classification, we use several convolution layers to transform the data and identify the patterns that we want. And then we flatten everything out and put a small, for example, 2 layers of dense network or fully connected, so that we build the actual classifier. Pooling is basically aggregating the outputs of a region into a single output, so that we reduce the size of the feature map or the data that we are passing on through the network. For example, max pooling, if we use a max pooling of 2 by 2 with a stride of 2, what we are doing is, starting from this 4 by 4 map here, we generate a 2 by 2 map where we take the maximum of each of these regions. So this allows us to look for, in this feature map, suppose that we had identified some particular pattern very strongly here. So we retain that information, but we are losing information about where in the input data we found the pattern. We know we found the pattern, but we are blurring out where we found it. This is something that can be important for the network, because you can imagine, as we are doing pooling here, so suppose that we have filters here that detect some particular edges or brightness or things like that on an image of high resolution, and we are looking at small regions because those are the receptive fields for these currents. When we do pooling here, we are reducing the resolution of the image. So we know we found some particular patterns, but now we are shrinking everything and bringing everything close together. And now here we can start looking for combinations of patterns that we found before, and shrink again, shrink again. So this does two things. One is we are increasing the effective receptive field of these neurons, because when we do pooling, we shrink everything, we lower the resolution of the image, while still preserving the information on which patterns were found at the previous layers. And the other thing is that we are abstracting from the position of where those patterns were found, and only looking at the information that they were found somewhere in the image. So when we do this, for example, this 6 and this 8 indicate strongly that the pattern was found, but we don't really care if it was found here or here or here or here, we just put an 8 there. And this means that the network can ignore issues like if there are some wheels, if they are here below or they are a bit above or a bit on the right and so on. It doesn't really matter. If there are wheels, then probably it's a car and not a boat. So that would be the kind of things that the network can use for the classification, and it doesn't really matter where the wheels appear on the image. So we may want to regulate the kind of pooling we make. Max pooling is an example. We can take the average, the square root of the sum of squares, or things like that. And also we may want to regulate overlap of pooling regions. For example, we could do something similar here by using a pooling of 3 by 3 and allowing overlap between the pooled regions. This would be an alternative way. So when you're doing pooling, you can also specify strides and the size of the pool. And this is an example this is an older example now from 2012, but you can see here the image has 3 channels and 224 by 224 pixels. Then you have here a convolutional layer with a receptive field of 11 by 11 pixels, and we have 55 filters here. And then we have max pooling to reduce the size of these feature maps. And then we have 128 kernels for the next convolution layer, and then again max pooling. So we are reducing the size of the image, so to speak, reducing the resolution there, but we are using more filters so that we can distinguish between more different patterns that appear there. And eventually, when we reach here, another max pooling, and then we have these dense layers here at the end. And typically, in a network like this, nearly all the parameters will be on the dense layers, because since they are fully connected, for example, here we have 2048 neurons and 2048 here, so we have 4 million connections between these two, right? And this is a lot more than what we have here, because here, for example, one feature map here, one of these neurons, has 11 by 11 by 3 weights, and we only have 55 of those. So even though we are creating large feature maps here, we have a lot fewer parameters than what we get on the dense net. So this is the general architecture for convolutional networks for classification. We do several convolutional layers to identify the patterns we need, and then we flatten everything out and put in some dense layers for the classification. Okay, so let's continue with the Keras Sequential API. To recall from last week, we need to import the classes we need to build the model. So in this case, we're going to use again the stochastic gradient descent, SGD. We need the sequential model, but now, previously we only used the dense layers. Now we're going to use two-dimensional convolutions, max pooling. We are going to use flatten to pass from the feature maps here, which are multidimensional, into the dense layers, where we need to put everything in a single vector. So you can put a flattened layer there to convert everything to a single vector. We're going to use dropout. Dropout it does that thing of switching off the neurons with some probability, batch normalization, and we can use the activation class to choose the activation for the layers. Although you can also usually put that in the actual construction of the layers, but this is just to show another way of doing this. So we can create, for example, for the convolutional network that we're going to use, it will be something like this. You create a model, you add the initial convolution, so this would be 32 kernels, 32 filters that you're going to create. With the 3x3 receptive field. By the way, the difference between the kernel and the filter is that the kernel is just the matrix that does the multiplication. The filter also includes the activation function. So, but the number will be the same because we have these 32 and then we add a rectified linear unit activation after all of those. Padding same means to pad the input with zeros so that the feature map has the same dimension as the input. We don't lose the edges there. And you need on the first layer to specify the input. So what we're going to use is this this data set here is a fashion mist. So the mist data set is a set of handwritten digits that were used for code, postal codes, identification, and so on. But those ended up being too easy for classification. So this is a bit more interesting, where they created this artificial data set where you have small cartoons of different types of clothing, and we want to train the network to identify one of the 10 classes of clothing. The images are the same as for NIST, the 28 by 28 pixels and grayscale, so they only have one layer at the end. And this is what you're going to use. So this would be the size of the input, 28 by 28 by 1. This is the shape of the tensor that goes into your network. And then you can put convolutions, max pooling at the end of all the convolutional parts. Note that there are some parts missing here. You can flatten everything out. So the feature map that comes here at the end is a large tensor with multiple dimensions. But since you want to feed this into a dense network, it needs to be just a single vector. So what flatten does is to reorganize all of these values into a single vector, and then you can put some layers here, dense layers, and so on. Here we can use dropout, batch normalization. Batch normalization, remember, does the standardization on the output of the previous layer before passing on to the next one. And so this keeps everything centered and with the same standard deviation, and makes it easy for the next layer to learn the important things, because the input is not constantly shifting everywhere. So, some hints on how to build your network. This is not really unanimous, but it's the general consensus. Use batch normalization after the activation function. So, for example, here we have a dense layer, we have a rectified linear unit activation, and then batch normalization. You could, if you wanted, to exchange this, normalize first and then the activation, but this doesn't seem to be as good, because the idea is that the input for the next layer is what is standardized, and not between the weighted sum and the activation of the same layer. Use dropout on the dense layers, and after batch normalization, because using dropout before batch normalization is a bit strange, since batch normalization is trying to keep a moving average of the activations of those neurons. And if you put dropout before, it's going to miss some values, and that may not work as well. So generally, we put dropout after batch normalization, and use dropout on the dense part of the network. Because dropout eliminates some inputs at random, or some neurons here at random, and using this on the convolutional layers would be a bit strange. Either it would mask parts of the feature map, or eliminate filters, and that may not work very well. So generally, use dropouts on the dense part of your network. Then, after you do this, you create the optimizer, like we did last week, and you create your model. So this would be, create model would be a call for a function where you have everything. This is I think a better way of structuring the code, because then you can always create the model at will just by calling that function. If you want, you can just put this all in the same script, it will work as well. But then we need to compile the model. So compiling the model, we give it the optimizer, we give the loss function, and in this case, categorical cross entropy is the one used for the softmax activation when we have a multi-class classification problem. And we have the softmax activation here at the end. So the end of our network is a layer of 10 neurons, because we have 10 different classes on the, where is the cartoon? I don't have here, but there are 10 different classes for the clothes in the fashion list. So that's there. And since each image can only belong to one class, then we are using the softmax activation. And the softmax activation, we use the categorical cross entropy. And at the end, after fitting the model, you can save the weights this way. I advise you to do this because next week we are going to use this model and apply this part to classifying lists. So the idea would be to use all these convolution transformations that are transforming the data of these clothes into some interesting features that the classifier can use. And we're going to reuse that and just retrain the classifier for list next week. So at the end, you can save your weights in this way. The fit method, as we saw previously, gives you this object that has a history field, which has a dictionary with all the different metrics that you use. And so if you choose these metrics, for example, accuracy, and if you fit with a validation data, so in this case, I use the test data for validation and the training data for training, because we don't really care about the true error of our model. This is just to play around a bit, and this data already comes separated into training and test. So you can use validation, the test data for validation. In a real application, don't use the test data for validation, leave it aside, because then it would be a biased estimate of the error. But if we do this, and since we added this metric of accuracy, in the history we will have the accuracy and the loss for the training data. So this would be the historic during training for every epoch. And we also have the accuracy and the loss for the validation data. And accuracy is the fraction of correctly classified examples. This is a good thing to have in classification because it gives you a general idea of how well the network is performed. Okay, so we're going to do two things in the tutorial. First is a regression with a simple multi-layer perceptron. So the one that you used last week, the same kind of thing with dense layers. The difference is that we have a linear output, so no activation function on the output. And you're going to use this data set for predicting the consumption of the car, miles per gallon, based on the different features. So I pre-processed a bit the data, so you have all the features in numerical values. I took out the categorical ones, and what you need to do is to standardize both the features and the target value. This is a good idea to avoid having values that range too much. You can also experiment not standardizing the target value, but in any case, you need to remember what you're doing and what kind of transformations if you want to use the network later. And then we only have 392 examples, so use 300 for training and 92 for validation. In a realistic scenario, you should set out something for testing, but in this case, we don't worry about that. And use one linear output with the mean squared error loss function, and then try different activations for the hidden layers, different momentum networks, and so on to experiment a bit. So this would be the starting part. Load the TSV that you have there on the tutorials page. Shuffle the data so that this is something that is especially important if you're going to do some separation like this, because you don't know how the data was sorted. Suppose that the cars were sorted by year on the data set. That means that you would have the validation set a range of years, and the training set would be a different one, and that would not be a very good split. So you can shuffle everything, do the standardization, and then split into training and validation, and then you can create a network, fit, follow the plots, and adjust the network to try to minimize overfitting and so on. The other exercise would be to use this fashion list dataset, which you can get from Keras, that command I showed you, which is this. Keras dataset fashion list load data. This will load the data, and it will give you the images and the classes for the training set, and the images and the classes for the test set. If you did not run this yet, it will download the data. It's about 20 megabytes. So I don't know how good the network is here. That's why I recommended you do this at home first. If you already did it, you have there on cache, and it will simply load it without a problem. Now, what we need to do is to reshape these matrices so that the shape of the images match what our convolution network is expecting. So we're going to use the reshape method here to get as many images as we have, because this is a matrix with all the pixels of each image in columns and each image as a row. And we want to change that to something that is 28 by 28 by 1 for each of the images. So this is as many images as we have, and then 28 by 28 by 1. So take that vector and put it on a three-dimensional matrix of 28 by 28 by 1. And the same thing for the test images. So the X is what we input into the network. Those are the images. And then we also need to change the categories. So we're going to normalize this, because all the images are between 0 and 255. We're going to change this to a floating point, float 32, and divide by 255, so they are all between 0 and 1, the brightness values for the images. And now we also need to change the classes here. So the class labels are between 0 and 9. There are 10 classes. But what we want to train is a softmax activation that has 10 outputs, and each output is the probability of belonging to one of those classes. So we need to compare that with a vector that has 0 on all the classes the image does not belong to, and the 1 on the class the image belongs to. Because that would be what our network will try to approximate to predict the class of the image. So to do that, we're going to use this one-hot encoding. Instead of having values 0 through 9, we convert that into vectors that have this kind of data. So if it belongs to this class, there is a 1 on the class this image belongs to, and zeros everywhere else. And this is what our softmax will try to approximate for this image, and so on for all the images. You can do that in Keras. You have these utilities, which is 2 categorical. you give the labels that you have, and you say how many classes there are, and it produces all of these vectors. So do this first with the training and the test labels, so that then you can use this on fit on the network that we designed with the softmax output. Okay, so the model for this exercise, I suggest you start with 2 convolutional layers with 3x3 kernels, ReLU and 32 filters, and then you can do batch normalization after these 2 layers, or in between the 2 layers too. Then use max pooling, and then in the second stack you can use an identical stack to the first one, but with 64 filters. So the idea in general on these convolutional networks is that as we use pooling to reduce the size of the tensors that we have in the dimensions of the original input of the image, we also increase the number of filters so that we compensate a bit the loss of that information, and we can detect more complex combinations of features in the input. So generally it works a bit like a funnel where it's narrowing here, but it's going longer and longer on the depth. So after putting these 2 stacks, you add a dense layer of 512 neurons, then the softmax layer with 10 neurons. Remember that before going into dense layer, you need the flattened layer so that you pass from the multidimensional feature maps into a single dimensional vector to go into the dense layer. Okay? So experiment changing with this, changing the optimizers and so on, and see what accuracy you can get on the validation set using these networks. So to sum up, we saw what convolution is and what convolution layers are in the neural networks, and how to do this with the Keras. You should consult the Keras API whenever you're doing these things to make sure that you're using the correct functions and see the parameters for the layers you have there, but you have all of this documentation online. Okay?